In this video, we will make the connection between X being a smooth variety and its cotangent sheaf being locally free. And the idea here is if X is a smooth variety of pure dimension n, then all of these tangent spaces, and thus also the cotangent spaces, have dimension n at all points of X. And on the other hand, we have seen that the cotangent sheaf, if you take the fiber at a given point, is just the cotangent space of X at the point P. So this we checked in this example here on spec R inside X. But since X is covered by these spectra, this is always true. So this is a sheaf, and its fiber at a given point is just a vector space, and it always has dimension n. So we expect that this is in fact locally free of rank n. And the next proposition says not only is this true, but it is also a unique characterization of being smooth. And so let's see the proposition. It says if X is a variety over K of pure dimension n, then this omega X is locally free of rank n if and only if X is smooth. And one direction, namely from left to right, is very easy. So if omega X is locally free, or in other words, omega X comes from a vector bundle of rank n, then, well, it's fiber at any point. Of course, I mean, by definition, around each point, this becomes a trivial sheaf, OX to the direct sum n, and so its fiber there is of dimension n. So this is just this statement here, but we have seen that this thing is isomorphic to GPX dual. This is for all P in X. But this means dimension of TPX is always the same. It's always n, which is also the dimension of the variety for all P in X. And then if you go all the way back to the chapter on smoothness, there was a lemma there, which implied that, well, if all the tangent spaces have exactly the same dimension as X itself, then X is in fact smooth. At all. In particular, I mean, being smooth just means it's smooth at all points. Okay, so this direction wasn't so hard. It was just using that we can reconstruct these TPX dual and then also the TPX from this cotangent sheaf, which we have already seen before. The interesting direction is kind of the other one, that if X is smooth, then actually this thing is locally free. So we need to be able to find the trivialization of this. So assume that X is smooth and P is an X. Then we want to show that omega X is locally free, but being locally free is a local property. That's exactly why it's called locally free. This just means it's a property which can be checked on an open cover. And so in particular, since X is a smooth variety, we can cover it by affine varieties. And so let's just assume from the start that X is such an affine variety. So in other words, X inside some AR is affine. Now we need a new variable because X is already of dimension n, so it must sit inside the space of different dimension. Okay, but then if you're an affine variety, if you go through this translation to the scheme world, it just means that you should look at the ring R equals AX, which is also the same as just the quotient of this ambient polynomial ring modulo some finitely generated ideals, let's say f1 up to fn, like this. And then we have seen, and this was, you want to look, this was example 15.3b. Like this, that the cotangent space at this point is just given. I mean, we can just calculate it from the equations. And in fact, it's just given by this k of dx1. Somehow it's an r-dimensional space, like this, modulo relations which just come from the Jacobi matrix. So these were coming from these partial derivatives of the generators of the ideal. At this point, I runs through the generators like this. And so so being smooth means that all the tangent space and the cotangent spaces have the correct dimension. So in other words, we know that TPX dual is of dimension n. So here we use the smoothness. But this means, well, this is an r-dimensional space, and we divide out by this subspace with these coefficients here. And if you express this in matrix form, then you have this Jacobi matrix, which is just the matrix having all these dfi by dxj p. So this Jacobi matrix must have rank, kind of the complementary number, so has rank r minus n. Because you start with an r-dimensional space, and then if you divide by the image of this matrix, and you subtract minus r minus n, so you get plus n. This is the right thing. Okay. So this happens at P. And this matrix having this rank here means we find the submatrix which has non-vanishing determinant it's the submatrix of r minus n of the rows and columns, for example. And so we can just assume that these are the last ones by kind of commuting coordinates. So assume that the submatrix of last r minus n rows and columns has non-zero determinant. And this determinant, so somehow these are now these delta fi divided by delta xj's. These are just some polynomials, right? And so this determinant, if we call this determinant h, then this is just an element in R. And we can certainly assume that at one of these points, this submatrix has the correct rank. But then this implies that if the submatrix of these last things has the correct rank, then you can use the submatrix to eliminate these last few entries here of the dxxi's, namely that the dxn plus 1 up to dxr can be expressed in the basis, which now is formed by the first one, dx1 up to dxn of tpx. So can use this matrix to eliminate the last entries, and then this forms a base. Now this happens all until now at exactly the point P. And now our goal is to make this a bit broader and have like an entire open subset of X on which you can find such a common basis. And the right thing to do is to look at this determinant, because somehow on the locus where this determinant can be inverted, you expect that you can still do this entire operation. So somehow on this distinguished open set DH inside X, you can, the determinant H is invertible. And so, in fact, you can't just express these things at exactly this point, but you can do this whenever you're allowed to divide by this determinant. This is just basic linear algebra. So you can express the dxn plus 1 up to dxr as a combination. So let me write as a linear combination of the first ones. And this linear combination, if you do the linear algebra, then the coefficients that you get here will exactly live in this localization. You're exactly should be allowed to divide by this determinant. Okay. And so this means that these dx1 up to dxn generate omega of this localization as an RH module. Right? We can express these remaining other generators in terms of these, just with coefficients in the ring. And so we already see, so we want to show that this is a free module with this basis. We already show it's a generating set. The only remaining thing to do is to show that there's no more relations. So this is the next claim. No relations. So this becomes a free R module. So this RH is isomorphic to RH times dx1 RH times dx and is actually free. It's a free module. And the proof, well, we just assume the converse. So assume there was a relation left. So assume that we could write G1 times dx1 n times dxn is 0. And these coefficients are now in RH, and they are non-zero. Right, I mean, somehow having a relation means at least one of them is non-zero. So let's say G1 is non-zero. And then our goal to show is that, well, this looks like we have one more relation between these generators. So at least at the point where this is really a non-zero relation, we can eliminate one more of the generators, and then we would get a smaller dimensional cotangent space, and this would be a contradiction. To make this precise, we just need to find now a point where we can really use this relation. And so by the Nullstellensatz, if this is a non-zero function, then we can find a point where it's non-zero. So in other words, there exists a Q in dH, D of H, with where this thing is actually non-zero. Okay. And then if we just write down what this relation means at that point, we evaluate this relation, then we get this. So we evaluated this, and so this is an element, this is 0 inside TQX dual. But now this here is a non-zero number in K, and these dx1 up to dxn, they generate TQX dual, because we already saw their generating set on this entire D of H. But this means they are generating set, but there's a non-trivial relation between them. So in fact, the dimension of this space is even one lower. So the dimension of at least one lower. So somehow the dimension of this is less than n. And this is a contradiction to the assumption. So all the way up here, we saw that all of these have the same dimension n because this is smooth of dimension n. And so we first get this contradiction to this assumption. So this means there's no relation. So this is a free module. So here we get that omega RH is a free RH module of rank n. And so this RH was, this spec RH was a neighborhood of this arbitrary point P inside X. And so these things cover all of X. On each of these covers, this becomes a free module. So the tilde thing becomes a free sheaf. And so we covered all of X by an open cover on which this omega X becomes free. And so this is just a definition of saying that this here is locally free of rank n. So this is the end of the proof. And the basic idea here is just that if you want to find this trivialization, just look at the Jacobi matrix, and then around each point you can find a submatrix which is of the correct rank, and then this allows you to find a basis of this free module basically around this point. Okay, so this was the full proof of this relationship, and now we can define finally the tangent bundle by saying if X is a smooth variety of pure dimension n, then well the omega X, we call it the cotangent bundle, not just cotangent sheaf, but now cotangent bundle, because we know it comes from a vector bundle of this dimension. And then if we take the dual, then we get the tangent sheaf or the tangent bundle of the variety. And so, I mean, we will not do so much with this, but just let me show here a baby example. If X is P1, like what is the cotangent sheaf and what is the tangent sheaf? Actually, we have seen those things before. Namely, omega X is just the twisting sheaf O P1 of -2. And then we saw in an exercise the dual of this tangent sheaf is O P1 of 2. Okay, and then in particular, what this shows is that if you take global sections of omega X, which would be something like, I mean, the sections of Tx are vector bundles, are vector fields. The sections of omega X are differential forms in the differential geometry language. So this would be differential forms on all of P1. And in fact, it turns out there are no such things, so except for the zero form. So this is saying there exists no non-zero algebraic differential forms on P1. We haven't really defined this this language, but if you have seen it before, then maybe you have seen such a statement here. And the proof uses more involved techniques for actually calculating these cotangent sheaves. If you're interested, this is proved in Gutmann's notes in these two things, which we're not going to see in detail. But this was just the first baby application. So what we're going to do in the last remaining video of this chapter is we're going to see an application of these tangent bundles and cotangent bundles to the classification of curves, projective curves over a field. We're not really going to prove anything there, but this is just to motivate, like, these things are actually useful. You can actually do stuff with them. And maybe as a nice conclusion of this chapter. Okay, so this is the next video.